We try to draw the relationship between determinants and inverse matrices in this video. First, let's give some definitions. Let A be a square matrix. The cofactor matrix of A is the matrix with the ij entry as the ij cofactor of A. The adjugate of A, denoted by Adj bracket A, is the transpose of the cofactor matrix of A. In other words, the ij entry of the adjugate of A is the ji cofactor of A. Let's look at an example. Let A be the matrix 4, 3, 2, 0, 6, 7, negative 2, 7, 9, and we want to find the adjugate of A and A times the adjugate of A. For the adjugate of A is the transpose of the matrix with entries Cij, where C11 is the determinant 6, 7, 7, 9, C12 is the negative of the determinant 0, 7, negative 2, 9, C13 is the determinant 0, 6, negative 2, 7, C21 is the negative of the determinant 3, 2, 7, 9, C22 is the determinant 4, 2, negative 2, 9, C23 is the negative of the determinant 4, 3, negative 2, 7, C31 is the determinant of 3, 2, 6, 7, C32 is the negative of the determinant 4, 2, 0, 7, C33 is the determinant 4, 3, 0, 6. Computing the determinants, we have the transpose of the matrix 5, negative 14, 12, negative 13, 40, negative 34, 9, negative 28, 24. After taking the transpose, we have the matrix 5, negative 13, 9, negative 14, 40, negative 28, 12, negative 34, 24. So A times the adjugate of A is the matrix 4, 3, 2, 0, 6, 7, negative 2, 7, 9 times the matrix 5, negative 13, 9, negative 14, 40, negative 28, 12, negative 34, 24. Performing the matrix multiplication, we get the matrix 2, 0, 0, 0, 2, 0, 0, 0, 2. As a result, A times the adjugate of A is 2 times the identity matrix. And in fact, 2 is the determinant of A, so A times the adjugate of A is the determinant of A times the identity matrix. This result is true for any matrix A, which we will prove in the following theorem. Let A be a 3 by 3 matrix. Then A times the adjugate of A equals the adjugate of A times A, which equals the determinant of A times the identity matrix. In particular, if the determinant of A is non-zero, then A is invertible, and the inverse of A equals 1 over the determinant of A times the adjugate of A. Before proving this theorem, let's first consider the 2 by 2 case. Consider the 2 by 2 matrix A with entries A, B, C, D. The adjugate of A is the transpose of D, negative C, negative B, A, which equals the matrix D, negative B, negative C, and A. So A times the adjugate of A equals the matrix A, B, C, D times the matrix D, negative B, negative C, A, which equals the matrix AD minus BC, 0, 0, AD minus BC, which equals the determinant of A times the identity matrix. Similarly, the adjugate of A times A is also equal to the determinant of A times the identity matrix. So the theorem is also true for 2 by 2 matrices. So that if AD minus BC is non-zero, then the inverse of A is 1 over AD minus BC times the matrix D, negative B, negative C, and A, as before. Let's try to prove this theorem. For simplicity, we write Cij as the ij cofactor of A for all I and j. The adjugate of A equals the transpose of the matrix Cij, which equals the matrix with entries Cji. So A times the adjugate of A equals the matrix Aij times the matrix Cji. The 1-1 entry is A11 times C11 plus A12 times C12 plus A13 times C13, which equals the determinant of A by expanding the determinant of A along the first row. Similarly, the 2-2 entry and the 3-3 entry are also equal to the determinant of A by expanding the determinant of A along the second and third rows respectively. Now, let's look at the off-diagonal entries. The 1-2 entry is A11 times C21 plus A12 times C22 plus A13 times C23. Let B be obtained from A by replacing the second row by the first row. Then the determinant of B equals 0, since the first row and the second row are identical. By expanding the determinant of B along the second row, we have 0 equals the determinant of B equals the determinant of A11, A12, A13, A11, A12, A13, A31, A32, A33, which equals A11 times C21 plus A12 times C22 plus A13 times C23. So the 1-2 entry of A times the adjugate of A is 0. Similarly, the other off-diagonal entries of A times the adjugate of A are 0. This implies A times the adjugate of A equals the determinant of A times the identity matrix. Similarly, the adjugate of A times A is also equal to the determinant of A times the identity matrix. Now, if the determinant of A is non-zero, then A times bracket 1 over the determinant of A times the adjugate of A equals bracket 1 over the determinant of A times the adjugate of A times A, which equals the identity matrix. Hence, A is invertible, and the inverse of A equals 1 over the determinant of A times the adjugate of A. The following theorem proves that we can use the determinant to determine whether a 3x3 matrix is invertible, which is the result that we want when we introduce determinants. More precisely, if A is a 3x3 matrix, then A is invertible if and only if the determinant of A is non-zero. We have already shown the if part in the previous theorem, so let's prove the only if part. By an equivalent condition of invertibility, A is invertible implies that A can be carried to the identity matrix by elementary row operations. Since the determinant of the identity matrix is 1 cubed, which follows from the fact that the identity matrix is triangular, so its determinant is the product of the main diagonal entries. So the determinant of the identity matrix is non-zero, and since A can be carried to the identity matrix by elementary row operations, we know that the determinant of A is also non-zero, which completes the proof.